For a modern naval radar operator, survival is a mathematical equation based on distance and speed. When a sudden return appears at the absolute edge of the radar horizon, moving at over a kilometer a second, the math breaks down. The ship has less than 30 seconds to react. This compressed timeline is the defining feature of the BrahMos. It is a supersonic cruise missile that leaves its launch cell with a specific engineering objective: to outrun a warship's automated defenses. Historically, weapons designers had to choose between two distinct flight profiles. Ballistic missiles, like the early V-2 rockets, travel on high-arching parabolic trajectories. They exit the atmosphere and rely on gravity to achieve extreme velocity, but their path is rigid and predictable. Cruise missiles operate differently. Driven by jet engines, they fly level within the atmosphere. They are highly accurate and can maneuver around terrain or defenses, but they trade speed for that precision, typically flying below the speed of sound. The BrahMos is built to inhabit both roles. It sustains the Mach 3 velocity, typically reserved for ballistic weapons, but does so within the lower atmosphere, guided along a precise, maneuvering path. This configuration challenges the baseline assumptions of naval defense. Systems built to intercept subsonic missiles must now account for a weapon arriving with almost no warning, moving too fast for mechanical turrets to track. Reaching Mach 3 near sea level requires immense thrust to overcome atmospheric drag. The BrahMos uses a two-stage propulsion system, igniting a solid fuel rocket booster immediately after launch to punch the missile through the sound barrier. Once the missile is supersonic, the burnt-out booster separates. A standard rocket engine burning an onboard oxidizer consumes its fuel supply almost immediately, limiting reach. To maintain supersonic speeds, it transitions to a liquid-fueled ramjet. This diagram shows an open tube lacking conventional mechanical parts. Instead, the missile's forward momentum forces incoming air against the center body, compressing it to extreme pressures, before fuel combustion provides continuous thrust. This thermodynamic cycle physically cannot function from a standstill. It requires high supersonic velocities to operate. It is the exact same principle used by high-altitude reconnaissance aircraft to maintain extreme velocities without melting moving engine parts. Through this design, the ramjet turns the very resistance of the atmosphere into the primary compression engine for the missile's sustained Mach 3 cruising speed. An object generating that much thrust and thermal energy should be highly visible to warning sensors. To delay detection, the missile executes a sea-skimming profile, descending just meters above the water. Because radar waves travel straight, the weapon remains shielded by the Earth's curvature. Near the horizon, signals bouncing off the ocean create multipath interference, masking the missile in background noise. By the time the missile crests the horizon and registers a clear track on the defender's screens, it is roughly 30 kilometers away. Traveling at Mach 3, that leaves the crew under 30 seconds to identify the threat, establish a lock, and engage. This chart visualizes the terminal physics of the strike. Looking at the equation for kinetic energy, velocity is squared. Because of this exponential relationship, a Mach 3 missile carries over 32 times the kinetic energy of a standard subsonic weapon. Mass and velocity dictate the final outcome. Even if a close-in weapon system acquires the target and shreds the missile at the last possible moment, the remaining 3-ton cloud of supersonic metal will still slam into the vessel's hull. The combination of sea-skimming and high kinetic energy creates a scenario where the ship is vulnerable even during a successful engagement. When a defender reacts, the momentum of the debris ensures that damage is likely unavoidable. This strike capability is the product of a military technical joint venture. Initiated in the late 1990s, the collaboration between India and Russia produced a platform that is now undergoing rapid iteration. Originally limited to heavy surface ships and land-based launchers, the system has expanded to airborne deployment. Heavy fighter aircraft like the Su-30 MKI can now carry the 2.5-ton missile, extending the weapon's reach far beyond coastal waters. Development is currently focused on the BrahMos NG. This next-generation variant compresses the physical length and weight of the missile by nearly half, reducing its radar signature and allowing it to be fired from the standard torpedo tubes of conventional submarines. These performance characteristics are specifically designed to exploit the physical limitations of current point defense systems. At Mach 3, The time to target is so short that many automated gun mounts struggle to rotate and track the missile before impact. The BrahMos demonstrates that raw explosive yield is secondary to speed and stealth. If a weapon can bypass a ship's sensors and defenses entirely, it doesn't need a massive warhead to achieve a mission kill. In modern naval engagements, the decisive factor is time. The BrahMos is engineered to consume that time, forcing a defender to react to a threat that is already upon them.